I'd like to introduce our speaker today, Dr. Madhur Nayan. He's a fellow in the combined Harvard program in Urologic Oncology. He went to medical school at McGill University and then completed residency at the University of Toronto. During residency, he was part of the Surgeon Scientist Training Program and completed a Ph.D. in clinical epidemiology and healthcare research. His research interests are in machine learning, and he has been appointed lecturer at the Massachusetts Institute of Technology to be an instructor for machine learning for healthcare. And this morning, Dr. Nayan will be discussing artificial intelligence for urologic oncology. So we're looking forward to your talk.
Yes, thank you so much for the kind. So it's an honor to be presenting Grand Rounds at Yale today, and I thank Dr. Kim for the opportunity. I'm really excited to talk to you about using artificial intelligence to improve active surveillance for prostate cancer. If you have any questions at any time, please feel free to interrupt me. I have no disclosures. So a question that we often face as physicians is to treat or not to treat. So I'm going to give you a very typical patient scenario that we see as a 65-year-old male with on active surveillance for grade group 1 disease. He was diagnosed 18 months prior, and he was found to have 2 cores positive. So already in your mind, you're beginning to calculate whether a risk assessment of whether you want to treat or not. And I know that because if I change the number of positive cores from 2 to 8, all of a sudden your risk calculation changes. And in your mind, you may be thinking you may want more information. So here's more information about the length of the cores, and you may still want more information to refine your risk calculation. So here's his PSA today, and here's what his PSA has been in the past. And you're continuing to refine your calculation in your mind based on this data. He had an MRI last week, shows no significant lesion, and an MRI 20 months ago showed the same thing. So you're further refining your calculation, but at the same time, you find it difficult to integrate all of this data in a meaningful way. And so you want to use a nomogram as a method to perform a more sophisticated calculation. And you find this one that was published in 2017 in BJUI that predicts grade reclassification, but it's outdated. There's no MRI included in this nomogram. And we know that MRI is routinely used in active surveillance. So this nomogram is no longer helpful. But imagine a world where you can use your AI algorithm. The AI algorithm tells you that using a federated learning algorithm, this patient's data has been compared with about 122,000 patients managed with surveillance at 140 hospitals. And it has taken a look at the MRI image from last week, compared it to the one 20 months ago. And although the human eye couldn't notice a difference, the AI algorithm found a very subtle change. It's so subtle, I'm pointing it out with a red arrow here. And that change, combined with an area on the pathology slide, it's able to tell you that the predicted probability of clinically significant disease is 98%. Furthermore, the model was last updated 5 days ago and has been calibrated to local MRI and pathology. Isn't this exciting? And so to talk to you about using AI to improve active surveillance for prostate cancer, I'm going to first tell you about how I became interested in AI for healthcare. I'll talk to you about what is AI. We'll talk about applications and limitations of AI for healthcare. And finally, I'll describe the use of federated learning to improve active surveillance for prostate cancer. So how did I become interested in AI for healthcare? I grew up in the suburbs of Montreal, and I went to medical school at McGill University. And early on in my training, I was interested in research. Initially, I wanted to be a cardiac surgeon, so I joined a lab, and we were looking at stem cells for cardiomyoplasty in vivo and in vitro models. But later, as my interest developed in urology, I began doing clinical research in urology. And as much as I enjoyed doing clinical research, I didn't really have a good understanding of it. I didn't really understand the statistics, but I still continued my interest in research. I started my residency in urology at the University of Toronto, but really wanting to get a deeper understanding of research methodology and statistics, I joined the Surgeon Scientist program at the University of Toronto, and I did a Ph.D. in clinical epidemiology and healthcare research. And during this time, I took extra courses in statistics that were outside of the traditional curriculum, as I was really interested in learning this aspect deeply. And my thesis was chemo prevention in kidney cancer. So we were looking at the use of commonly prescribed medications like metformin or statins that may have anti-neoplastic properties and evaluating whether their use was associated with outcomes in kidney cancer. Now, this is a topic that had been studied before, but I had a particular methodological focus on comparing different methods of modeling use. So some people had looked at ever versus never. So if someone had taken a statin at any time in their life versus those that had never. But I found this to be a very crude assessment. A patient that had taken a statin for 1 day would be grouped in the same category as those that had taken it for 5 years. And to me, this kind of grouping seemed biologically implausible. And so another way to sort of differentiate those that have been using the medication for longer or not is to dichotomize this at a certain cutoff. But this cutoff is often chosen arbitrarily, and it's biologically inconceivable that someone who's on one side of the cutoff to someone who's slightly over the other side of the cutoff to be drastically different in their risk assessment. And so another way to more robustly model this is to model the continuous use. And often people assume that there's a linear relationship between the exposure and the outcome, but often biologically this is not true. And so a way to account for this is to model the exposure in a non-linear fashion. And this may seem more biologically plausible. So this is what I focused on in my PhD, was looking at the non-linear association between medication use and outcomes. And so the approach that I used was fractional polynomials. This allows for 44 different possible transformations of the functions. And so these models are much more flexible than a linear model, but are they flexible enough? There's 44 possible transformations. Does every biological relationship fit in one of those 44? Probably not. And so towards the end of my PhD, I began to learn about machine learning, and that this offers the most flexible approach of modeling. And I learned that according to the universal approximation theorem, the neural networks can fit any continuous function. So I came back to residency and completed my residency at the University of Toronto, but I was really interested in developing my skills in machine learning. So I chose a fellowship where I could do that. I went to Harvard, and in my research year, I focused on machine learning by taking machine learning for healthcare at MIT. Now, I did not have the prerequisites for this class. So in the time between residency and the start of this class, I had to teach myself and get myself ready. So I read this book, An Introduction to Statistical Learning. I strongly recommend it for anyone that wants to get introduced to machine learning. I had to teach myself Python programming. Fortunately, during my PhD, I did a lot of programming in SAS, so this was not too difficult of a transition. But nonetheless, this was the hardest class I've ever taken. I spent many nights working on probability theory. And I struggled, but I really pushed myself. I worked hard, and in the end, I got an A. And I'm really excited that this year I'm going to be one of the instructors for the class. Okay, so now moving on to what is artificial intelligence. When you see pictures like this, it's not surprising that artificial intelligence is one of the most exciting topics these days. It seems to be like a panacea. And if we look at the number of publications on PubMed that are related to artificial intelligence or machine learning, they are growing significantly over time. And so given the proliferation of articles in medicine related to artificial intelligence, we're going to go briefly into some of the math behind these models. And you may think to yourself, well, you're not a computer scientist. Why do you need to know some of the math behind these models? And I think that question is best addressed by Eric Topol, who's the author of this fantastic book. It's called Deep Medicine, How Artificial Intelligence Can Make Healthcare Human Again. And I strongly recommend this book to anyone that's interested in seeing how AI will influence healthcare. And so there's two passages that stuck out to me, and I'll read those to you. Future doctors need a far better understanding of data science, including bioinformatics, biocomputing, probabilistic thinking, and the guts of deep learning neural networks. Much of their efforts in patient care will be supported by algorithms, and they need to understand the liabilities to recognize bias, errors, false output, and disassociation from common sense. Okay. So what is artificial intelligence? Some other terms you may have heard are machine learning and deep learning, so we'll dissect those in this slide. So the term artificial intelligence refers to teaching a computer to behave like a human. And this term is not novel at all. Actually, it was coined in 1956 at the Dartmouth conferences. An approach, there's two different types of AI. There's general AI. This is where a computer is really behaving like a human. And this is what you've seen in some movies. So it sort of looks like a robot who's able to sense, reason, act, and adopt. And we are very far from achieving general AI. What we've achieved so far is narrow AI, where a computer can perform a specific task like a human. And so examples like this include self-driving cars, teaching a computer to beat a human at the game Go, recommender systems, and even the Gboard on your phone is based on narrow AI. How do we achieve AI? One approach to do this is machine learning, and machine learning at its most basic form is an algorithm that learns from the data to perform a specific task. And machine learning had made some progress from the 80s to up about 2012, but not much progress had been made, and that's why this field really wasn't that hot prior to then. Until a revolutionary study came out in 2012, which we'll talk about, that used deep learning, and deep learning is a subform of machine learning, and that's where a lot of the breakthroughs in AI have come from, is using deep learning. So this is a study that really revolutionized the AI world. This is from Jeffrey Hinton and his group at the University of Toronto. And there was a competition called the ImageNet classification. And using a deep learning approach, they found that their model had performed significantly better than previous state of the art, which was based on traditional machine learning approaches. This paper has been cited over 92,000 times as of January of this year. And you can see here that back in 2012, the top 5 accuracy was about 85%. We've only continued to get better. And the latest update is of November 2021. The team at Microsoft has now the top 5 accuracy of 99%, far surpassing that of human performance, which is 95%. Okay, now we'll move into some of the applications and limitations of machine learning for healthcare. We'll talk about prediction models. We'll talk about computer vision, we'll talk about clinical notes, and then we'll talk about surgery. So starting with prediction models. As I mentioned, machine learning is a much more flexible approach to modeling than traditional statistical approaches. So I wanted to evaluate whether we use a machine learning approach to predict progression on active surveillance, whether that would be improved compared to a traditional statistical approach. Prostate cancer, as everyone knows, is one of the most common cancers diagnosed, and most patients are candidates for active surveillance. But currently, there are no robust models to predict those that are having progression. A robust model can allow for risk-stratified surveillance protocols. So in this study, we determined whether a machine learning approach could improve prediction of progression on active surveillance compared to a traditional statistical approach. So for this study, we did a retrospective review of 790 patients managed at the Mass General Hospital with active surveillance. There were 15 features that we used in the model. These were demographic, clinical, and disease characteristics. And we compared a traditional statistical approach, which is logistic regression, which most people are familiar with, and used an automated variable selection strategy. In this case was specifically backward selection. And we compared it to 4 alternate machine learning approaches. These were support vector machines, random forest, a fully connected artificial neural network, and a machine learning version of logistic regression. So just to note, logistic regression can also be applied in a machine learning approach. So we will go into some of the mathematics behind how a artificial neural network works. And I'm inspired by Dr. Topol's words that I presented to you earlier on why physicians should understand this. Okay, so here is a artificial neural network and I think it's really important to understand this because this was the architecture behind the breakthrough study in 2012 that led to all of these significant improvements in AI. And it's the reason behind self-driving cars. So I think it's an important model to understand. So here shown are the neurons and synapses. The circles represent the neurons and the arrows represent the synapses. In the blue, we have the input layer, the first layer of the network. And in the last layer, we have the output layer. In between are known as the hidden layers. So here is the first hidden layer and here is the second hidden layer. Now we are going to zoom in on this neuron. So we've zoomed in on this neuron. It has 3 inputs coming to it. That's shown here. These are the X's. Each input has an associated weight, and each neuron has a bias term. In the neuron, the product of the inputs and the weights are summed. The bias term is added, and this value is plugged into an activation function. And there are different kinds of activation functions. Examples include sigmoid, ReLU, SOP+. And after plugging it into the activation function, we get an output, and this output is transmitted to the subsequent neuron. So let's see this in action. Let's say our input for our model predicting progression on active surveillance, we put in age, race, and PSA. These are the values for our individual patient. He's 65 years old. As race, we'll use a binary indicator. He's 0, and his PSA 3.6. The weights and biases terms are learned from the neural network through a method called backpropagation. The weights and inputs are they're multiplied and they're summed, and the bias term is added, and a value of 1.49 is obtained. We use this value of 1.49 on the x-axis of the activation function, and we get a y value. And so that is used as our output for this neuron. And that output then becomes the input for the subsequent layer. Any questions so far? Okay, so coming back to our study using machine learning to predict progression on active surveillance for prostate cancer, here we are showing the F1 score. This is one of the performance metrics that is often described in machine learning studies. You may be more familiar with terms like sensitivity or specificity, or the C statistic, but the F1 score was chosen here because it takes into account the class imbalance. And so here what we see is that all of the machine learning models had a significantly better F1 score than the traditional statistical approach. And the highest performing machine learning model was the support vector machine. Now the F1 score ranges from 0 to 1. And so even the best model only had an F1 score of 0.6. So overall, our study was the first to evaluate machine learning to predict progression on active surveillance. And we found that a machine learning approach outperformed a traditional statistical approach. However, we did not achieve a robust model despite using machine learning. Why? Because we didn't have a high quality data set. There was a limited number of patients, about 790, and a limited number of features that were used in model development. Okay, moving on to computer vision. So what are some potential benefits of computer-assisted interpretation of images? There can be near instantaneous reporting of results, and so potentially having an earlier diagnosis may result in earlier treatment and potentially improved outcomes. There's the consistency of interpretation because the machine will constantly make the same prediction over a specific image every time. And then there's reducing barriers to access. So computer vision can be applied to low and middle income countries and improve care in those places. So let's take an example of diabetic retinopathy. Diabetes is an extremely common condition around the world, and around 30% of patients affected with diabetes have retinopathy. And so there's a significant need for screening. It's currently recommended annually, but there is limited access. So automating this process would be of significant benefit. And there had been approaches using images to detect diabetic retinopathy with traditional machine learning, but this lacked specificity. Then in 2016, Gulshan and al. Were the first to apply deep learning approach, and they found that they were able to obtain strong sensitivity and strong specificity for detecting diabetic retinopathy. Now, this was not a simple task. They trained the algorithm using approximately 130,000 images from 70,000 patients, and they required 54 ophthalmologists to label the images. Just to give you a sense as to the amount of resources that are really required to train a robust algorithm. And so building up on this study was another group that they developed a deep learning algorithm to detect diabetic retinopathy. And they compared the performance of an autonomous AI algorithm compared to humans. So they took 819 patients with diabetes, had them assessed by an AI system, and then compared that with the human expert, which served at the gold standard. And they found very strong sensitivity and specificity for this AI system. This led to the approval of the first autonomous diagnostic AI system authorized by the FDA in any field of medicine, without the need for a clinician to also interpret the image or results. How about in prostate cancer? Deep learning has been applied for prostate MRI. This is a study from a group in Germany. They evaluated 312 patients, 250 of whom were used for training. And they found no significant difference in the sensitivity or specificity between the algorithm and radiologists. For prostate pathology, deep learning has also been applied. In this study, they took a random selection of about 8,500 biopsies from 1,300 patients from the STH-LM3 trial, and they found that grading between the algorithm and expert pathologists was relatively within agreement. Going to clinical notes now. So clinical notes are a critical component of clinical data, as we all know. Up to 80% of clinical data is estimated to be in clinical notes. Why is so much clinical data in the notes? Because written text remains the most natural and expressive method to document clinical events. So it's easy to document our clinical information in notes, but this is a problem for research analysis because text data cannot be used by computers relatively easily. And so what has traditionally been done is that humans have read through the text, extracted meaningful information, and processed that into structured data. But that is a laborious process, it's costly, and once that human is finished, that update is no longer valid, and it takes another human sometime later to update it again. And so a way to automate this is to use natural language processing. And this is teaching a computer to interpret text. And so one application of natural language processing is information extraction, which is basically parsing through unstructured text data, extracting meaningful information, and translating it into structured data. So here, to illustrate this as an example, we have a prostate biopsy pathology report, and the relevant information has been highlighted. You can create rules to extract the information such as primary grade, secondary grade, T-stage, end stage, and margins. Other applications of NLP include text classification, name entity recognition, word sense disambiguation, conference resolution, and ranking. And traditionally, NLP was approached from a rule-based methodology, and more recently, machine learning has been used for NLP. And some advantages of using a machine learning approach include that it can automatically identify regularities from the annotated data, and it can generalize to previously unseen similar patterns if it's trained with sufficiently large data. And so, looking at this application of NLP to prostate cancer, this study looked at using NLP for extracting information from prostate biopsy pathologies. They compared a rule-based approach to a machine learning approach, and they evaluated which would be better. And it turns out that it actually depends on the context which one would be better, and that is if it's trained in a single institution data, then rule-based outperforms machine learning. But in a multi-institutional data, machine learning outperforms rule-based only. The combination of rule-based and machine learning outperforms either approach alone. And clinical text data can also be used as part of multimodal modeling. So in this study that predicted in-hospital mortality for ICU patients, they found that combining the word embeddings from clinical text data with the structured data, such as laboratory values and other numerical values, that the clinical text data significantly improved prediction of mortality. So there really is a lot of hidden wealth, I would say, in our clinical text that is currently not being used in prediction modeling. And moving on to surgery, one application of machine learning to facilitate surgery is anatomical landmark recognition. And so this is a study that was developed by a group at Stanford. They developed a deep learning algorithm called CystoNet, which is able to detect bladder tumors on cystoscopy. And so to train this algorithm, they had 141 videos from 100 patients, and they found the per frame sensitivity was 88%, and the per frame specificity was 99%. Another exciting application of machine learning for surgery is autonomous surgery. And now I know that this might sound like it's out of the movie, but it may actually be possible through an approach called reinforcement learning. And reinforcement learning is a machine learning model where an agent learns strategies to accomplish a task. And this is a study that was published in April this year, made a lot of news headlines, where a robot teaches itself to walk using reinforcement learning. In another study, this study from UCSD, they created a reinforcement learning environment for the Da Vinci robot. And this study, they trained the robot arm to perform specific tasks, including reach and pick. And then they applied this to a real world scenario, a simulated surgery, not an actual patient. But they then applied this to a suction device that was able to evacuate debris, and then to a needle driver, which was able to collect debris and then transfer it to the assistant. So there's some very preliminary research, but I do think that sometime in the long distant future, we may see a role for computer-assisted surgery. Other applications of machine learning to surgery include surgical phase recognition. So this can help annotate the videos and can really facilitate education. And then finally, there's gestures and error recognition, and this may help with technical performance of surgeons in evaluating their technical performance. And so these are some of the exciting applications of machine learning to healthcare, but we're still not quite there, and that's because there are still several limitations. And these include lack of high quality data, generalization, and fairness. So going back to the study where I used a machine learning approach to predict progression on active surveillance for prostate cancer, despite using machine learning, unfortunately, we did not achieve a robust model. And as I mentioned, I think this is partly because of the lack of high quality data. This was a single center study, limited sample size, and limited features used in model development. And so when I say limited features, one example of this is that we only considered baseline data. So for example, when we modeled PSA, we only took their PSA prior to diagnosis. To me, it's clinically conceivable that the PSAs that they had prior to that would also be informative. Another aspect that we were missing was the digital imaging or the histopathology data. So we had abstracted, for example, the grade group, the length of the cores, and that is a crude assessment of the histopathology. But what if we could actually use the images in our modeling? In the time of my fellowship, I knew that I wouldn't be able to include the actual digital imaging or the histopathology data. There's a lot of processes involved to get these digitized, but I thought I could improve the model by augmenting the baseline data. I thought I could use longitudinal data, and this would be very exciting for a machine learning algorithm called a recurrent neural network. So in a recurrent neural network, the output at a certain time can be used as the input at another time. So coming back to our example of active surveillance for prostate cancer, we can model the longitudinal PSA, and I think that this would be much more informative than using a single measurement of PSA. Similarly, you can imagine that you can model the MRI taken recently and compare it to any MRI taken in the past, similar with biopsy pathology. So my idea was to apply recurrent neural networks and augment the baseline data. Another thing I thought I could do to augment the model was increase the sample size. So how could I do this? One way is to manually update the Excel database that I'd received, look up all the patients that had been on active surveillance, manually review the charts, extract the data, put it in the Excel database. But in my opinion, this is an old way of collecting data and has a lot of issues. It's labor intensive, it's static, it's prone to error. And really the way that we need to think about collecting data in healthcare moving forward is a more automated process. And so the way that I envision this is that we have a collection of code that processes our electronic health record data. The advantage of this is that it allows for consistent data across users, and it can be updated relatively easily. A disadvantage of using a collection of code is that the data can be noisy. So when you have a human going through the charts, they can pick out discrepancies that may not be relevant and correctly annotate the data. But when you have a computer algorithm, it may not learn that as much. So for example, if you have a prostate biopsy code after a radical prostatectomy code, us as physicians know that there's something wrong with that. But a computer, if you're just searching for prostate biopsies, would include this patient, even though they may not necessarily should be included. And so it's really important that when you're using a collection of code to validate what's happening behind it. So I wanted to do this with our Mass General Brigham data and develop a prostate cancer database. They have a database called the Research Patient Data Registry. And I think this is one of the best databases out there. As I've worked with several databases over the last 10, 15 years of doing research, and I really think that this is an excellent resource. So there were over 80,000 patients with a prostate cancer diagnosis over the 28 years that are included in this database from 2 large tertiary hospitals, the Brigham Hospital and the Mass General Hospital. And there's detailed data. There's information on labs, pathology, radiology, diagnoses, etc. And all of this is longitudinal. This is a really fantastic source. And there's also the possibility to integrate the digital images, the digital pathology. It's really a wealth of data. So my original study using the Mass General database that had been annotated only had 790 patients. Using an automated approach to identifying patients, we identified about 1,700 patients, and we used a rigorous definition. Patients on active surveillance were those that had a prostate biopsy showing malignancy followed by another prostate biopsy. I think this is very specific. Not sensitive, but for the purpose of our study, we wanted those that had another prostate biopsy. So although we were able to identify this cohort, we were still missing critical data because the pathology data is all in text, all in unstructured format. So how are we going to get this data? One approach was the traditional way. We'd have a human go through all of the pathology reports, extract that information, but that has many limitations. And so what we did was we applied natural language processing. As the slide I showed you earlier, that applied information extraction to a pathology report that was developed by us for my class project at MIT. And we were able to develop this algorithm that's able to extract grade from about 96% of pathology reports. And its accuracy is about 95% from randomly audited reports, which we think is very strong. And as easy as I made it look on the last slide, it actually was a significant effort because the way of reporting data in text format is not yet standardized. And so here are 10 ways that I found in the pathology reports of describing pathological stage 2 without actually specifying PT2. Even more challenging is extracting PSA from those. There were many, many ways that PSA was described, and this makes it very challenging for a computer to extract this meaningful information. So as we were developing these algorithms, I became frustrated, and in that I tweeted this, that until there are standardized methods to report clinical data, I will write my notes as if they will eventually be abstracted for machine learning. I'm kindly requesting others to do the same. And I think that, in this generation, we really need to think about how we're going to collect data moving forward and maybe adjust the way that we are collecting it currently. Okay, moving on to generalizability. So models developed in a specific environment may not work well in a different environment, and I think that's well illustrated by this picture here. Clearly, this algorithm that was used to detect blinking was not tested in heterogeneous populations. And this concept of models developed in one environment not working as well in another is not unique to machine learning. This is a study that was published in 2002 that evaluated whether the Parton nomogram would work as well in a community-based population. And they found that while the nomogram performs adequately in a community-based cohort of men, it did not attain the success demonstrated in previous studies in select academic cohorts. And this is a bigger problem in deep learning given the number of parameters. And so this brings the problem of overfitting. And a more practical illustration of this is how will the system perform if the MRI at the hospital that the algorithm is trained at is different than the MRI that I'm using at my hospital. And so I think there's going to be a lot of exciting deep learning algorithms that are being developed at various institutions, but to apply them to the local hospital, the hospital systems will need to fine-tune the externally developed machine learning algorithms. And really what I think, to go a step further, what they'll need to do is they'll need access to their local high-quality data to fine-tune the externally developed machine learning algorithms. Finally, moving on to fairness, it's really important to assess how these machine learning algorithms are working for different populations. And so this was a study that came out in 2019, made a lot of headlines because they found that a machine learning algorithm that was being used by a very large health insurance company to allocate resources was actually negatively biasing those that were Black. And so it's really critical to assess how these algorithms are working in different populations, because machine learning models learn from the data they are trained on and are therefore prone to bias. So I wanted to evaluate this in prostate cancer. So I did a study that was looking at predicting survival after radical prostatectomy and evaluating whether the performance would vary by race. So I used the NCDB, which is a database composed primarily of white individuals. And I evaluated whether the performance would vary, testing the model in different race subgroups of white, Black, and non-white, non-Black patients. And then I also wanted to see whether we could improve that performance by adjusting the population in which the model was trained on. So for example, if we train the model in only non-white, non-Black patients, does it perform better in those patients than using a model trained in a more heterogeneous population? For example, perhaps the model trained in the race subgroup would be more suitable for that specific patient population. And so here is the F1 score for the different models. As we can see, the race imbalance model had an F1 score of 0.51. The worst performance were in those that were non-white, non-Black, such as myself. And surprisingly, the best performance was found in Black patients. And then when going back to the non-white, non-Black subgroup, evaluating whether adjusting the training environment, whether it was a race imbalance, training in the race subgroup or race balanced population, we found that the performance did not meaningfully change. And this was shown across different races. And so really what this shows is that the model's performance was relatively invariant to the race composition of the training subgroup, which was surprising to me. And what this suggests is that the variables that were included in the model, the standard ones that are available in the NCDB, are more predictive of the outcome in white and Black patients compared to non-white and non-Black patients. And so really what this brought out to me is that developing robust algorithms within subgroups can be challenging, particularly when they represent a small sample size. And this illustrates the potential for AI to perpetuate discrepancies in care, emphasizing really the importance of evaluating performance in patient subpopulations. Okay, moving on to the last section, using federated learning to improve active surveillance for prostate cancer. So I think everyone here will agree that the key to becoming a medical specialist in any discipline is experience. But how do we get an AI algorithm to gain experience? Well, AI learns and gains experience from large, varied, high-quality data sets. This is the problem because such data sets are scarce in healthcare. I've worked with many databases during my research time, and they really are difficult to find. Even RPDR, which has the potential, still requires a lot of work to process that. So what's the solution? We can try to tackle the lack of high quality data sets, as I described in my effort with the Mass General Brigham prostate cancer database. And to give the AI algorithm a large, varied experience, I think federated learning is the way to go. And I'll talk to you a bit about that. So creating large, high quality data sets, the traditional approach, human extraction, is inadequate, as I described, for many reasons. I really do believe that the current and future directions is automated data curation. This is through a collection of code. And what I envision is a clinic to algorithm pipeline. So a patient will come to the clinic, and by the end of their visit and some short time thereafter, that data that has been collected at that visit, their PSA, their MRI results, is already in the database. So it's been collected in a way to automate that collection and that processing. And I envision a multimodal data, so not just clinical variables, but we have digital imaging, we have digital pathology, we have all the notes data. And I really think that robust algorithms using machine learning is going to take advantage of all these modalities. Now, in terms of experience, the traditional method has been different hospitals sharing their data. However, this is inadequate. Sharing PHI carries significant risks, and in healthcare, there should be a better way of sharing this data. And now I'd like to introduce you to federated learning. So federated learning is an approach that uses machine learning that allows an algorithm to learn from different devices without actually sharing the data between the different devices. And this was introduced by Google in 2017, and they actually use this approach to improve the Gboard that is on many people's phones these days. So to illustrate how federated learning works, so as an example here, we have 3 different hospital systems. We have MGB, we have Yale and Stanford. They all have their private data, and rather than them sharing the data directly with each other, they train a local model. The parameters of that local model are sent to a decentralized server. That decentralized server then takes the model parameters from the different sites, refines the model, and then sends back its updated parameters to each of the individual hospitals. Those individual hospitals will then readjust their parameters to the local data, and it keeps going back and forth until an equilibrium is reached to the ideal model. So to illustrate this in another way, the central server chooses a statistical model to be trained. It transmits the initial model to several nodes, which is hospitals. The hospitals train the model locally with their own data, and then the central server pulls the model results and generates one global model without accessing any of the data. Has this been applied to healthcare? Actually, very recently, this came out in September. So they used data from 20 different hospitals around the world to predict oxygen use among symptomatic patients with COVID-19. And they found that using a federated learning approach improved the average AUC by 16%, which in my opinion is a clinically meaningful improvement. So coming back to our original patient scenario, imagine a patient, 65-year-old on active surveillance with grade group 1 disease. His other information is shown here, and you have access to an AI algorithm. It looks at the MRI data, considers the histopathology data, applies federated learning, and tells you the predicted probability of finding clinically significant disease. Thank you. I'm happy to take any questions, comments, discussions.
Madhur, this is Michael Liebman. I just want to say that was a really sensational talk from the beginning to the end. So thank you very much. I was intrigued. What do you think is kind of the, in a model looking at progression on active surveillance, where do you think that the greatest sensitivity would be between institutions, between centers? It strikes me that how much of a concern or challenge is variation in image acquisition, the calibration of the scans locally?
I think that is a huge challenge in machine learning, is the local calibration of a model may not work for other populations. And so that's why I think it's very essential for each hospital to have their local data, have access to their MRI imaging that are digitalized. And these models will have to be adjusted for the local parameters and constantly be adjusted as the MRI images change, as the technology adjusts, as the treatment changes. I think all the models will have to be continuously updated.
Madhur, I have a question for you. So does all the information have to be in a digital format? I mean, one thing that you had shown was the, I think you called it NLP, natural language processing. And you showed how computers can kind of pick out kind of keywords and kind of simulate like a whole model from it. And we use Epic, and a lot of our information is digitized, but then we have all this information that comes in scanned in as a PDF format. And so, for instance, someone comes to the office and I'm looking for PSAs, and the ones that are digital I could find easily. And then the ones that are in PDF, I'm searching through the chart, and you really have to be kind of like a detective to kind of find things or look in old notes that have been scanned in. So can computer learning search PDFs as well?
Absolutely. So I ran into that problem when I was developing a model predicting biochemical recurrence after radical prostatectomy using our MGB database. Similar to Yale, we're a referral center, so a lot of our patients come from outside. We don't have their PSA values in Epic. They're often scanned in. And so that's a great discussion. How do we get that information that is not available in our digitized systems into our database? And I think there's two ways of thinking about it. One is to develop algorithms to process those scanned PDFs. I think that's one approach. Another approach is how do we have a system that takes the information from the scanned PDFs and process it into our system in a meaningful way. Currently, it's only available in the scanned format, but what if we had a process that all of the relevant information from that was able to be extracted and put into Epic? I think those are different approaches, but certainly something that needs to be thought about as we work in a referral center, and a lot of the critical information is in the scanned documents.
Hi, this is Mike C., one of the fellows. I have two quick questions. The first is, from a regulatory perspective, I know that, at least from my limited understanding, a lot of machine deep learning is considered black box learning, where we don't know the actual process of what's going on, and we only subsequently compare the machine's output with our personal experience or with our recognition of the image to get and know if it's correct or not. So how do you see that playing into getting FDA approval for a lot of this? And then the second question is, at least Google, and I think a lot of other chip makers are moving more to AI on physical chips and specific devices as opposed to a cloud-based system, like the tensor chip, for instance, in the new Pixel. And how you think that might play into like machine learning in the EMR versus robotics. Are we going to have more of like local machine learning versus just like a whole cloud system for the entire health system?
Yeah, so the first question on interpretability, I think, is one of the limitations of machine learning in healthcare. I didn't have time to really go into it. And this is a field that is of significant research these days. A lot of people are trying to unblock those boxes and trying to make them more interpretable. But even with that, there's discussion of whether that's sufficient. So for example, one method of applying interpretability to deep learning is class activation maps on imaging. And so this highlights particular regions of an imaging that are informing the model. But as you mentioned, the only way that we as humans are able to process this is if it fits in with our preconceived ideas. So if we look at a chest x-ray that's supposed to predict pneumonia, and we see that the region highlights with what we think is related to pneumonia, then we agree with it. But what happens if a deep learning algorithm highlights an area that us as humans haven't yet come to appreciate? And so what some people argue is that interpretability may never actually be achieved because our understanding of biology is somewhat limited. And what we really need to do is to evaluate its performance in different populations. And that's how we will achieve an acceptable model. So if the model works for different populations, then does it really need to be interpretable? I know that that's controversial. But that has been one opinion expressed, is that these models may never really be interpretable. We just need to ensure that they work for different populations. And then the other question, I may not have understood it completely, and feel free to repeat it, but in terms of cloud-based data versus wearable data from wearable technology, is that my understanding?
No, more like, sorry, that is like the new Google Pixel phones, like the tensor chip, their new systems-based architecture is supposed to be optimized for AI processing on the phone, as opposed to processing the AI on the cloud and then inputting the results back to the phone. And just, I mean, that's sort of like maybe a random question. Just, do you see that sort of playing into a role in healthcare, and how you might see that happening, or is that just something that is like we're not there yet?
Yeah, I'm not sure if I see the application of that directly to healthcare, but I'd be curious to learn more about it.
Hi, great talk. Thank you very much. So seems like you outlined a few different hurdles before we get to actuation of some of these technologies, what are the things that we can try to do, or is there anything that we can try to do? You mentioned reporting our notes in certain ways. How can we move this forward on an individual practitioner's basis?
Great, thank you for that question. I had received a similar question from some of my colleagues that I worked in clinic with. They saw my excitement for this and they wanted to see how we can sort of start making changes now. And I do think it starts with the way that we start thinking about data. So earlier someone asked about the PSA from the scanned notes. So how do we put that data in our clinical note? I think we need to all think about it, doing it consistently and in a similar way. I think practically speaking, it would be good to start in a specific disease space, in a focused area. For example, active surveillance. We have the whole department writing a clinically consistent note. And with time, we find that there are some things good about it, some things that are not so good about it. And we refine that process until we all agree that this is a great way of collecting data on active surveillance and processing it. And then we move that to other fields and really standardize the way that we write our notes. The way that I'm currently writing my notes is I have basically data sections, which are very point form and just descriptions of data, and then more other sections where I write more text that I'm able to interpret the data. And so I think if we all put our clinical notes in that sort of structure, where part of it is just data, PSA value date, PSA value date, PSA value date, and then you have another section that is more of your interpretation, I think that'll really facilitate that collection and processing.
So I have a question. So it looks like I think for this to, or this, the AI coming into part of medicine. So then the question is, how early do you start training? So does this have a role in medical school education? So like, where is it going? Harvard adopting any sort of a part of the curriculum for medicine coming in, discussions happening? Because the concept you described, it's going to take a lot of time for us to understand.
Yeah. My understanding is that there are starting to be some introductory lectures in medical school relating AI to healthcare, but I do think that early adopters will be starting to integrate themselves now. I think if trainees have time, they should learn programming, as I think this will help them be involved in AI research. But I do think that in 10 years this is going to be a big part of what we do day to day.
Additional question is, it strikes me that there are a lot of shared goals and shared challenges, and I'm wondering how much are health systems doing piecemeal. It seems that like every department is taking this on separately. Is there a way to align all of these goals if the from Epic, we have, every health system has probably a huge IT infrastructure. Have you been able to work with the broader Epic IT side of things?
I think that's a great question. A lot of what I'm applying, a lot of what I'm saying doesn't apply just to urology. It applies to all disciplines. And what I've seen some hospital systems do very recently, this is all a recent trend, is have a department that's related to information technology. And I think, I'm not sure if Yale has that yet, but I think that's where it would start, is where we have a standardized approach, the entire health system, in terms of collecting and processing data. I think Kaiser Permanente has a system like this, but I think Yale at the higher level needs to adopt an approach where all of the data for the entire university is collected and processed in a standardized way, so that if someone in medical oncology, for example, wants to study patients with metastatic bladder cancer, they can query a system that processes that entire EHR data and gives them a data repository of patients with metastatic bladder cancer, for example. And so this is a collective effort of physicians, programmers, all people to write this and come up with this unified code to identify the different cohorts. But I agree, this is not just a urology level effort, it should be something higher up.
I'm not sure how much you've heard, we do have something called the Joint Data Analytics Team, or JDAT, which is kind of a warehousing of the EPIC backside data, which can be very powerful.
Excellent. I look forward to hearing more about it.
Yeah, the university and the health system have also collaborated on something that's being referred to as it's the data lake, which essentially is every piece of information about patients, digital images, digitizing path, information from the Generations project, which is a sequencing project, structured data, notes. It's a massive set of data for every patient that's been treated in the health system.
That's fantastic.
If you're interested, you should check out the profile of a guy named Wade Schultz, who's he works at the Core Center for Computational Health, which is the Center for Outcomes Research and Evaluation. I'll when we meet later today, I'll show you his profile.
Great, thank you.
I think he's on your agenda. This visit or
Okay, great. I've had a chance to look at some of the initiatives at Yale, the core movement, the Yale Open Data Access movement. I think those are fantastic. One of the goals I didn't really mention in this talk, but I think if we're really going to make significant advances in machine learning, we can't just do it in isolation. We need to have an open data access. The ImageNet challenge was an open data source, and that's how groups around the world were able to compete and build better and better algorithms to reach 99% top 5 accuracy. I think if we want to build the perfect MRI detection algorithm, it's going to be an open data movement where different groups around the world are building more and more robust algorithms. So I'd be excited to collaborate with the Yale Open Data Access movement to help streamline that with prostate cancer.
Well, I'd like to thank Dr. Nayan for the wonderful talk today. And you can always reach out to him if you have any further questions after this meeting today. So everyone have a great weekend, and see you next week.